Mindsetters, welcome to today's Grade 10 Physical Sciences show. Today we have a special revision lesson on chemistry. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter at LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Well, let's look at question 1. It says to us, draw a picture or a diagram, symbolic representation, to show the micro view of an aqueous solution formed when the solute is copper 2 chloride, ammonia, and lead chloride. Okay, so we're going to draw 3 little pictures. The first one is for copper 2 chloride. Now, what do we know about copper 2 chloride? Well, the first thing that I know that copper 2 chloride is a salt, and it has the formula CuCl2. It is ionic, so when it dissolves, it's going to dissociate. The positive ions are going to be left surrounded by little water molecules, and the chloride ions, and there are 2 of those, are going to be hydrated as well. So that's the chemical equation, which I didn't really ask you for, but it's a nice way to think about it. How are we going to picture this equation? Draw a picture of this part of the equation. We're not interested in that, we're interested in this part. So what's it going to look like under a microview? I'll tell you what I'm going to do. I'm going to draw the copper as little orange blobs, and I'm going to draw the chlorine as little white circles. Recognize that this is positive, recognize that that's negative, and then what we're going to do is we're going to draw in the water around them. So around the positively charged water copper ion, we're going to get, and there was 2 pluses over here, sorry I didn't put those in, we're going to draw the water molecules, and you could draw 3 or 4 or 5 or 6, it doesn't really matter. But the idea is that they're surrounding them. But look what happens on the other side. Here is our little water molecule, and it's now going the other way. Why is that? Well, because it's attaching to a negative ion. It's surrounding a negative ion. We're going to squeeze in another water molecule over here. We're going to put in the positive ends closest to that, positive ends closest to that one, positive ends closest to that one, and so on. So what you can see is that the water molecule forms this bubble. It kind of like wraps up the ions, and that's why we call them hydrated ions. And in the equation, that's why we do this, AQ, because anything that's dissolved in water is given the name of an aqueous solution. Aqua, if you think about aquarobics, what other words can you think of, Looney, that have the word aqua in it?
Aqueous cream.
Aqueous cream, very good. Cream that you rub, that's so nice when it gets dry and you want to rehydrate you. It has aqueous or aqua. Think about some aquanaut. There are a whole lot of other words that we could talk about as being aqueous. Now, remember, this was ionic, so we recognized we've done one like that. But this one, ammonia, it's NH3. It's a covalent molecule. But we know that ammonia is polar. You should know this. It is a polar molecule. And here's a little bit of a rule that starts to come up when we talk about dissolving. Things that are of the same nature. So if we've got something that's polar, then it will dissolve in another substance that is also polar. We say like dissolves like. So ammonia, covalently bonded. So if we're going to draw the equation first of all. Ammonia now actually interacts with water in a slightly different way. It doesn't just split apart to form nitrogen and hydrogen, but it forms the ammonium ion. There are no ions here. This is usually a gas, and water is usually a liquid, and it forms ammonium ions. We're going to say that's AQ. And then on this side, we're going to say what's left over is OH minus, and that's also AQ. So what's actually happened, guys, is that ions have formed. In the dissolving process, we have made ions. This process is not called dissociation, because when we had, think about, you form an association, you join a soccer club, you become a member, you associate yourself. When you want to leave, you say you dissociate, you distance yourself. You don't agree with their politics anymore, so you dissociate yourself. You move away. For ionic solids, dissolving in water, they undergo dissociation. Association. For covalent substances like ammonia, they undergo ionization. And they can ask you both of those terms. You need to know them. So please be very aware of the difference. But if we were to draw a picture, well, it would be more or less the same sort of thing, except that the geometry is slightly different. So let's just draw a very brief one, and we'll try and get it in. We'll say that's the ammonia, and let's put an oxygen with it, or a water molecule. We want an extra hydrogen. Remember what we said? It needed to be in the solution. So we want an ammonium ion, and that's positive overall. And over here, we're going to have another oxygen. We're going to have an oxygen with a hydrogen attached to it. Let's make them all the same. And in between these, this is negatively charged. We put those as negatively charged. In between those, we're going to have some water molecules. And the water molecules are just normal water molecules that haven't lost anything. So in this case, you're going to have water molecule surrounding it like a little tube, like a little bubble, and we get those forming in solution. Now you'll notice that in this case, we've got a lot more water molecules than ammonium. Remember, this was your nitrogen. There's your ammonium with the 4 dots around it, the 4 hydrogens. The other things are the water molecules that are surrounding it. Ammonia is covalent, it forms ions, it dissolves. You can't see a little bunch of ammonia molecules creeping up in a corner. No, they're not allowed to do that. They stay by themselves. Now, the last one that we have to look at is this one. Now, unfortunately, we didn't have time to discuss it in the summary, but we might as well discuss it now. Lead 2 chloride. Guys, it's a metal and a non-metal. That tells us that it's a salt. If it's a salt, its bonding is primarily ionic. So we've got lead ions and chloride ions in a crystal lattice. The trouble with most, with a lot of ions, with a lot of salts and crystals, is that they're actually quite hard to dissolve. Lots of things water will dissolve. So like all nitrates, all group 1 and some of group 2 salts of those elements, water dissolves. But there are some that it will not dissolve. Like most carbonates, water doesn't dissolve. Sulfates, most sulfates will be soluble except for some of the heavy metals like mercury, barium, and lead. And chlorides, most chlorides are soluble except for silver, lead, and mercury. So you can see that there's a pattern here. We've got lead chloride. And what we're going to say is it doesn't dissolve. It is insoluble in water. So it will not dissolve in water. Why? Why won't it dissolve in water? Well, because the forces between the lead and the chloride are stronger than millions and millions of water molecules tugging at each of those little ions. Can't break them down. They're too tightly bound. So if we were to draw a picture, what we'd recognize, first of all, if we were asked to do an equation, we would say PbCl2 and plus water basically doesn't do it. There's no reaction. There's no reaction. Nothing happens. That's solid. that's a liquid. There might be a very, very slight 1 in a billionth of one of these break apart, but in general, nothing. So what we're going to do is we're going to represent it. We're going to say, well, there's lots of water, and they would be surrounding this clump of ions. And those clump of ions make that one the lead one, make this one the chloride one, and we'd recognize the 2 chlorides for every lead, and they're just going to stay very tightly mashed together in a lovely lattice. Okay? They're not going to break apart. They're going to stay in their solid form. Forces are too strong. Right. So, just to summarize, water is a solvent, sometimes called the universal solvent, can dissolve ionic things, solutes, can dissolve covalently bonded substances as well, particularly polar covalently bonded substances. Water is very polar, but it can dissolve even a slightly polar substance. Ammonia is also very polar, so it dissolves very easily in water.
I think it's time for a break now, so don't go away. We'll be right back. Welcome back, Mindsetters. Even though we are selecting highlights from previous shows, you can still follow me on Twitter @LearnExtra, or you can post or comment on our Facebook page. Now, let's do some more revision.
So what we're starting with is the idea of having some silver nitrate. Now, silver nitrate reacts with a sample of potassium chloride, which is called sample A, sodium iodide, which is sample B, and lithium bromide, which is sample C. So guys, here we've got it. We've got 3 test tubes. If I had to draw them, just let's make some space here and let's get some pictures going. So here we've got sample A, sample B, sample C. Now remember what they told us was that the first one, sample A, was potassium chloride. So I'm going to put down KCl. And then this next one was a B, sodium iodide, and the last one was lithium bromide. So sodium iodide and lithium bromide. Okay, and we've got these in a little test tube like that, and now we add a few drops, just a few drops of something called silver nitrate. So there we go. So we're putting some silver nitrate into that, we're putting some silver nitrate into that, and we're putting some silver nitrate into that. And what I want you to understand is that we've got to apply our solubility rules here. Remember, we said that all nitrates are soluble. So we know that these drops of nitrate, of silver nitrate, they're soluble, they dissolve. And we know these are group 1 metal cations, so they're soluble. So there's going to be no bits and pieces. But look at something interesting. If I add silver to sodium chloride, silver nitrate, I'm going to add silver ions, Ag plus, and I'm going to have floating around in the solution some Cl minus. Now guys, what you need to understand is what we said about the chlorides. All chlorides are soluble except for the silver chloride. They don't like to dissolve. They're not very soluble at all. And in fact, what happens when these two get close to each other, they kind of stick together. Okay? And I've stuck them on top of each other. It's not really right to stick them on top of each other, but let's hope that we can just stick them next to each other like that. We're going to make some silver chloride. And silver chloride is a white precipitate. So at the bottom of the beaker over here, we're going to make a whole lot of milky stuff, and the solution is going to go white. Okay, that's what we're going to see if we add silver nitrate to potassium chloride. We were asked to predict what else would happen. Predict what you observe for each of the other samples. Now, if you have your notes in front of you, then we'd be able to say, well, what will happen if we have silver nitrate and sodium iodide. Now, all the halogens all the halide salts of silver are not very soluble. And they're different colors. The silver chloride is white in color, the bromide is a creamy color, and the iodide is a yellow. It's almost like a canary yellow. It's very nice to see. And so we're going to shade that in and say, you would notice at the bottom of this test tube is a yellow precipitate. And in the last one, we're going to take the silver nitrate and we're going to add it to the bromide. Now, I can't get the color right, and I haven't got the option to have more colors. Maybe I do. Let me see if I can get some custom colors. I want a creamy one. I want one that's a little bit over there, maybe a little bit less yellow. Maybe that's it. Add to custom. Let's see. Yeah, we're going to do that one. We'll say that's okay. And let's hope that we've got it. You know what? It's not working. I want that one. There we go. I've got it. And we've got a kind of not yellow and not white. And that's your bromide. Okay? But some people find it difficult to tell the difference between this one, and this one. And so chemists have done some experiments. And they found some other tests that we can do to distinguish those. I've written about those in the notes, and let's see if we've got some chance to deal with that. So we've done our predictions. What would you observe? We'd observe precipitates forming. Look at what the next question says. Now, even if you didn't know those precipitates, I hope you can now deal with the balanced equation for the reactions that take place for each sample. So let's do this. Sample A, we know that we've got potassium chloride. We know that we've started with silver nitrate. What are we going to be producing? We know that these were in aqueous solution. That was aqueous. What are we going to produce? We're going to produce silver chloride. Valencies are the same. Silver is +1, chloride is -1, but they form a solid. And what's the other stuff that's still left in aqueous solution? Potassium nitrate. Is that soluble? Yes, it's very soluble. Remember what we said. All nitrates are soluble, and all salts of group 1. And potassium's particularly soluble. So potassium nitrate is very soluble. It's one of the most soluble things. If you compare other things, they might be soluble, but if you've got a group 1 and a nitrate, they're the most soluble. So look out for that. Okay, next we go to, that was in sample A. What about the equation for B? Well, in B, we had silver iodide plus sodium nitrate. Notice the balancing isn't a problem because they're all +1. And we just must put in aqueous. We must put in aqueous. And what we're going to say, we produce silver iodide, which is our yellow precipitate. That's the solid, plus sodium, not potassium. Let's read the question. Plus sodium nitrate. And that's aqueous. It dissolves. It's very soluble, and so we don't have a problem with it. Well, what about the next one? We made lithium bromide. We started with lithium bromide at least, and we're going to make some silver bromide. So we started with lithium bromide, and we added some silver nitrate, just a few drops, and that was in aqueous, AQ, standing for the fact that it's dissolved in water, and we made silver bromide plus some lithium nitrate, and that was still dissolved, aqueous, whereas the silver bromide was solid. Check everything is balanced, and yes, it is. So we've done the hard work. We've identified and we've written the balanced equation. Next question. Let's go. What type of reaction occurs in each? Well, this isn't that difficult, guys. Think about it for a minute. What have we done? We've taken two aqueous solutions, added together, and we've got something falling to the bottom. We call that a precipitation reaction. If you had said ion exchange, you would also not be wrong. So precipitation, ion exchange. Precipitation is the more obvious one. Now, last one, identify the insoluble salts that form. Well, we've done that. We did it right at the beginning. We said that one in A was silver chloride. There we've got it. And in B, it's silver iodide. And in D, it's silver bromide. Easy stuff, but so useful. We could go to that stream in the Middle Olifants catchment area, and we could take along some silver nitrate and start to test, are there excess chlorides, bromides, or iodides in the water, just by adding a few drops. Now, it's important to note that when you do this test, you also must add acid, because there is something else that is insoluble. Silver carbonate. We didn't have time to discuss this in our summary, but silver carbonate is very insoluble. It is insoluble. So what we need to do, it also messes up our results. It makes a white precipitate and it interferes with our results. So what we've got to do is we've got to add acid. And if we add an acid, it will dissolve the carbonate and produce carbon dioxide. It will have a gas evolving equation. It will produce carbon dioxide and the precipitate disappears. But if we add acid to any of these precipitates, any of these, they're going to laugh at the acid. They're not going to disappear. They're going to stay there. But there's something I want you to think about. You need to make sure that you add the correct acid. Think about it. We added, to make it a fair test, we added silver nitrate. We know that silver chloride produces a white precipitate. So we must be very careful not to add any more chloride ions. We could use any acid, but probably the best one to use in this scenario would be one that doesn't have extra ions. So nitric acid would probably be my favorite. The one that you want to avoid, you would never use hydrochloric acid. Because if you used hydrochloric acid and you added HCl here, you know what would happen? You would just get more white stuff forming. And then you'd be really confused, because not all of the silver ions would necessarily have precipitated. Now, I've been talking too much. Let's move on, because we've got another part to this question. So Paula, who was the person doing this experiment, can't decide if one of the precipitates is cream or yellow. Now, this is obvious. This is a common problem. We sometimes find that the precipitates aren't very distinct. If we've got a high concentration of the iodide ion, then it will be very clear. It will be canary yellow, and it stands out very nicely. But if there's not so much, and we could get confused. So what do we do? So she adds a few drops of carbon tetrachloride. Now, carbon tetrachloride is very poisonous, it's dangerous, and it's carcinogenic. Carcinogenic means that it can form cancer. There's been research to show that it's not a very good thing to use. So it's better that we do it just as a test on the board here. We can use alternatives like trichloromethane instead of the tetrachloro, but the trichloromethane is an alternative. The colors are slightly different with trichloromethane though. So this organic liquid forms a separate layer with the water. She then adds chlorine, water, and shakes the mixture. So the carbon tetrachloride turns pink. Now, I want to show you what's going to happen in this scenario. And it's really interesting, and it's a really nice thing to see if we can get this done. So here is our solution. And she couldn't make up her mind whether the original thing was cream or yellow. So she takes some of the original unknown. Notice that there's no precipitate here. So she's just taken from the original solution. And one beaker. And then she adds carbon tetrachloride. Now the carbon tetrachloride is more dense than water, and it forms a layer that's separate at the bottom. So there's my carbon tetrachloride, CCl4. In here is my unknown. I don't know what it is. I suspect it could be a bromide or an iodide, and I'm not sure. This is my unknown. And the next thing that she does, she then adds chlorine. Chlorine water. Chlorine dissolved in water. Now, chlorine is a very strong oxidizing agent. It's one of the more reactive halogens. And in fact, if we look at group 7 on the periodic table, you'll see it's fluorine, chlorine, bromine, and iodine. And that's on group 17 or group 7. We call it 17 at the moment. These are halogens. And what we recognize is that they are all wanting to gain an electron. So if we put them in, they're going to take electrons away from something else. So chlorine is more reactive. So if there is bromine in it, or if there is iodine in it, then chlorine comes along, and look what it will do. If there was a bromide ion, which is sitting happy and comfortable because it's gained its electron, it's in a neutral state, just like the noble gases. It's got to be like the noble gas at number 18, filled outer level. Chlorine comes along and says, it's not fair, you've got the extra electron, I'm going to take it from you. And so chlorine takes the electron away from the bromine, and we're going to need 2 of those, and chlorine then becomes chloride, and there are 2 of chlorides, and bromine has got no alternative but to turn back to Br2. Okay, so that's the process. This is what sort of reaction? Transfer of electrons. It's a redox reaction. Now the interesting thing is that the bromine, if it's non-polar, and we spoke about polar and non-polar last week, and what we know is carbon tetrachloride is non-polar. So bromine dissolves very easily in the organic layer, and it turns a nice color. The difference between these two, the reaction, if it was bromine, would do that, will produce bromine. If it was iodine, would be exactly the same chemical process. Chlorine and iodine, sorry, let's just correct that. We'd have iodide ions present. Iodide, 2 of them. Chloride, the chlorine would become chloride, and the iodine would become the iodide would become iodine, and this dissolves in carbon tetrachloride and gives us a pink solution. So in the question, what we were asked is what substance caused the organic layer to turn pink? It was iodine. Iodine. Where did the iodine come from? It came from this redox reaction. I want to finish the question. Redox is the answer. Write a balanced chemical equation for the reaction, and I've done it already. There it is. Hope you can see it. There it is. And we're done.
Okay guys, I hope you are enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away, we'll be right back. Welcome back from the break. Let's not waste any more time and get straight back to today's revision lesson.
Here we go. Question number 1. We're looking at some concepts about the mole. And in question number 1, it says the following. A helium balloon contains 2,4 grams of helium gas at STP. Now, all it's telling us is that, remember, that means we can use that the volume of 1 mole is 22,4. That's when you see STP, that's what you know that you can use. Okay, so it then says to us, how many moles of helium are there in the balloon? Well, we're going to say we've been given something about the mass. Okay? We don't know anything about the volume at this stage. So we know it's helium. So if we're given mass, we need to work with the mass equation. We're asked the number of moles. Number of moles is mass over molar mass. So where do we go? We're going to go to the periodic table, and always make sure you've got your periodic table out so you can see there the big number at the bottom is the relative atomic mass of helium, which is the molar mass of helium, because helium is a monatomic gas. It exists as molecules of a single atom. Noble gas doesn't combine with anything. So I'm going to say to you, the molar mass of helium is 4 grams per mole. So we want the number of moles. We know that the number of moles is mass divided by molar mass. And the mass that was given, here we go, we were given the mass, there it is, take it off, 2,4, divided by 4. Now, you could use a calculator, but you should really know that 4 into 24 goes, how many times? 6, yes, so that's 0,6. And what is this? 0,6 mole. Let's just check it on the calculator and make sure the calculator is working. So we're going to say, there we go, let's just choose that one and make sure that we've got the calculator up. In fact, turn it on to select, and we're going to say 24, clear. See, that's why I wanted to check the calculator. 24 divide, oh, so it wasn't 24, it was 2,4. 2,4 divided by 4 gives us 0,6. So my answer wasn't incorrect, it was in fact correct. Let's move on to the next part of the question. And we want to go to this one. It says, what is the volume of the balloon? Now, guys, what you need to understand is the balloon will blow up and increase or decrease in terms of its number of moles present. The temperature and pressure, we're told, was at STP. So we don't have to worry about that because it's hot day, it's going to get bigger. No, this is at STP. So we're now going to use the volume formula, and we're going to say, we know that the equation says on the data sheet, the number of moles and volume are related as follows. The number of moles is equal to volume divided by molar volume. We want to find volume. God, the important thing here, so that you don't lose marks, is put down the formula as you see it on the data sheet. Don't try and change it. There's a mark for getting the correct formula. So put it down. And then the next thing we're going to do is we're going to do the substitution into the formula. We're going to say the number of moles is 0,6 is equal to the volume divided by the molar volume. The volume of 1 mole is 22,4. So what is the volume? Therefore, the volume is equal to 0,6 multiplied by 22,4. And I'm not going to chance this in my head. I'm going to use the calculator. I'm going to say 0,6, which is on the calculator, times, let's just turn the smart ink off for the moment, times 22,4, and we get an answer of 13,46. Now, if you're not sure whether you've got the right answer, let's think about it this way. 0,6 is very close to 0,5. And 0,5 is a half. So if we take half of 22,4, We know that's going to be about 11,2. Well, it is 11,2. Easy to do that. So we can expect the answer to be a little bit bigger than 11,2. And yeah, it's 13,44. It looks like it's the correct answer. So we're going to write that down, 13,44 decimeters cubed. That's quite big. Remember, 1 decimeter cubed is 1 liter. 1 decimeter cubed is equivalent to 1 liter. So we've got 13 liters. This is quite a big balloon. Okay? But notice something, that it had only a small mass, only 2,4 grams. So you can see that even though we've got a very small mass, it's very big volume. Helium itself, we know, is not a very dense gas. The particles move apart from each other, and that's why we use helium to lift balloons and use them in dirigibles and all that sort of thing. Okay, let's move on. We want to link now, do the third link, and it says to us how many helium molecules are present in the balloon. Now, this isn't a trick question. Remember, every molecule of helium is actually an atom of helium. So we recognize that if we can find the number of atoms of helium atoms, then we found the number of molecules. The number of atoms are related in the following way. The formula on the data sheet is the number is equal to the number in the sample, number of moles is equal to the number in the sample divided by Avogadro's number. We use that by substituting in what we know. And we know that we've got 0,6. We know that Avogadro's number is 6,022 times 10 to the 23. Let's just lift that up so that we can see a little bit easier. And we want to find n. So now that you've substituted, and you would get a mark for giving the right formula, you would get a mark for the substitution, you might even get a mark, another mark. The important point is we can say therefore the number of molecules, remember molecules and atoms for helium are the same thing, but it asked you about molecules. Molecules of helium is equal to 0,6 multiplied by 6,022 times 10 to the 23. Right. Let's do that on the calculator. Pull out the old calculator and let's clear that first of all. And we're going to say 0,6 times 6,022 exponent 23. And there we've got the power, and we get the answer of 3,6132 times 10 to the 23. Now, we only need to write to 2 decimal places, so I'm going to write 3,61 times 10 to the 23. Say 3,61 times 10 to the 23 atoms or molecules, but because the question asked me for molecules, I'm going to write down molecules of helium. I just have one thing to say to you here. Guys, remember that if they gave you a diatomic gas, so something like oxygen or helium, I'm sorry, not helium, hydrogen, or even chlorine or fluorine, or one of those that's diatomic, then you're going to need to adjust. The number of molecules is not the same as the number of atoms, but here we know the number of helium atoms is equal to the number of helium molecules. And that's a very important thing. It is just simply H. Doesn't combine with anything. And for that purpose, we know that we're dealing with a molar mass of 4 grams per mole. If we were dealing with a diatomic gas, then the molar mass would be double what you see on the periodic table. Okay, let's move on. We're moving to question number 2. The next part of this, in this question, what we're dealing with is a concentration question. We're told that we've got 25 centimeters cubed aqueous solution of sodium chloride. is made up using 4,8 grams of salt. So the first thing they say to you is, what is the concentration of the solution? Now, we need the number of moles. Concentration is moles of solute divided by volume of solution. So we've got the volume of the solution, but we haven't got the number of moles. So we're going to have to find the number of moles of sodium chloride. I like to put down what I'm doing as a subscript. So I'm going to say the number of moles. What were we told about the solute? We're told that it's salt, it's sodium chloride, and we've given a mass. The number of moles is equal to mass divided by molar mass. So let's work out the molar mass of sodium chloride. Go to the periodic table and let's pick it out. So on the periodic table, we're going to say, over here, we've got sodium, 23. We know the formula is NaCl, so 23 plus 35,5. We're going to add those two together to get the molar mass. So we're going to say 23 plus 35,5. And again, you can use the calculator to do this, and it always is useful to check yourself. I also like to estimate 23 plus 35,5, and you're going to see that it's about 55, and there we go, 58. That's right, because 3 plus 5 is 8, and 2 plus 3 is 5, so we get 58,5 grams per mole. So we now know the molar mass. What we've got to do is we've got to find the number of moles first of all. So let's get the number of moles. We know the mass was 5,8, and this one was 58,5. So what's the number of moles? I hope you can see that it's not going to be difficult. It's 5,8 divided by 58,5, and there it is, 0,0991. Now, remember, you've got to round off to 2 decimal places. And even at this stage, you round off to 2 decimal places. Don't use the whole thing on the calculator. So to 2 decimal places, I realize that the third place is a 9. I'm going to round that off and so say that the answer is 0,10. So let me write that in. I'm going to round that off and say this answer is 0,10 moles. I'm going to just get rid of that so I've got some more space to work with, because the next part of the calculation is the key part. The key part, we're going to say concentration is the number of moles divided by volume. The number of moles, 0,1, and the volume was given as 250. Now, do you think I can leave it as 250? No, it said centimeters cubed. What is concentration units? Mole per decimeter cubed. So I must change it. How do I convert from 250 to decimeters cubed? Well, you know that 250 milliliters is about a quarter of a liter. So that was a terrible 5, 0,25 decimeters cubed, divided by 1,000. So I'm going to do exactly that over here, and divide by 1,000 and get my answer. So I'm going to say 0,1 divided by 0,25 equals 0,4. So 0,4 moles per decimeter cubed. That's the concentration. That's the concentration of the solution. Now says to me, notice how it leads on. How many ions of sodium are present? Well, I started with sodium chloride. Do you remember what happens when sodium chloride, salt, table salt, dissolves in water? Yes, it dissociates. We can write it as NaCl solid in an aqueous solution will go to form Na plus Aq plus Cl minus Aq. So what do you notice in this case? Remember, for every 1 mole of that, I'm going to produce 1 mole of that. So if I know that I had 0,1 moles of that, don't you think it's true that I have 0,1 moles of that, of the sodium ions? Absolutely, because the ratio is 1:1. Notice where I'm getting it from? There's the number of moles present. Always go back to number of moles. So moles, and now it says how many ions. So now I'm going to say the number I'm looking for is the number of ions. I'm going to use the formula that's got number in it. And so let's substitute into that. What do we know? We know that we can say, therefore, 0,1 is equal to the number that we're trying to find times Avogadro's number, or divided by Avogadro's number, is 6,022 times 10 to the 23. And we can then get, therefore, N is equal to 0,1 times 6,022 times 10 to the 23. Now, that's not too difficult to do. You can even do it in your head, because if you divide, you multiply by 0,1, it's like dividing by 10. If you divide by 10, you're going to knock down one of those powers, and the answer, I'm just going to put the answer up here, is going to be 6,022 times 10 to the 22 ions of sodium.
Thanks for joining me and for chatting to me during the show. Please visit our website, learn.mindset.co.za, to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through the year, so stay connected. Goodbye.